Hello everybody, my name is Shady Issa, and in this video I will be talking about our new range locks and their different usages, which is a joint work that I did with Alex Kogan and Dave Dice from Oracle Labs. To give a quick introduction, range locks are a synchronization mechanism that was conceived in the context of parallel file systems. The idea was to allow different threads or processes that are writing to the same file to execute concurrently as long as they are accessing disjoint regions. So if each thread or process acquires a lock that protects a given range, only threads with overlapping ranges would be serialized, allowing more parallelism between non-overlapping ranges. This concept can be extended to any shared resource as long as we can define ranges over it. So we can use range locks to protect concurrent data structures, can use them in databases, and like more recently, there has been a growing interest within the Linux kernel community to try to use range locks to protect the address space, to tackle one of the scalability bottlenecks in the memory management subsystems. And this was like the main motivation that started our work. However, existing range locks have several limitations. So for instance, the range locks that are being proposed in the Linux kernel community rely on an auxiliary red-black tree data structures to store the ranges that are currently being held or requested. So for a thread to acquire a range lock, it needs to insert a node describing this range, like as its starting point and ending point and its access mode, like whether shared only or exclusive, into the tree. And to synchronize the concurrent accesses to this tree, there exists an internal spin lock, which with large number of concurrent range lock acquisitions, it becomes a scalability bottleneck in itself. In this work, we are presenting a new design for range locks that's actually lock-free in the common case, and thus is capable of supporting large number of concurrent range lock acquisitions. We also devised a new approach to support parallel virtual memory operations inside the Linux kernel. However, we did not stop only there. We also showed how range locks can be used to efficiently synchronize accesses to concurrent data structures with skip lists as a concrete case. However, due to the shortness of time, I will not be able to cover the last point, and I would refer you to the paper for more details. So what's the basic idea behind our range locks? Basically, we're like going to replace the internal red-black tree data structure with a linked list that would store the ranges that are currently being held, sorted by their starting addresses. So when a thread wants to acquire a range lock, all it just needs is to insert a node describing this range into the list. And because this list is sorted, any two ranges with that conflict or overlap, they would always be competing on the same insertion point. Therefore, we can rely on the hardware support for compare and swap atomic operation to ensure that at most one of the conflicting ranges can be inserted at a time, while other ranges that fail in the compare and swap, when they retraverse the list to find the insertion point, they would observe the conflicting ranges and just would be blocked waiting for it to finish. And with this design, range locks can be acquired without any internal locks, which can allow higher scalability than the existing designs. To extend this design to support read and write semantics, compare and swap operation is not enough anymore. Consider this example that I'm showing here. We have this list with those currently held range locks, and here green refers to shared or read-only ranges, while the red is of course update ranges. So if we have these two new range lock requests that actually do overlap with each other, they will not be overlapping in the insertion point anymore. And why is this? It's because readers are allowed to overlap. So actually the point of insertion is different, and both of them would manage to insert their nodes into the list, which is a data race that would break the correctness of our algorithm. Luckily though, we can solve this data race by an extra validation step that can be executed after a successful compare and swap operations. And I will refer you to the paper for more details on this validation step. But the point here is that we can still support read-write semantics without any internal locks. As a matter of fact, we only defer to acquiring internal locks to support or to handle the starvation and fairness issues. Now, putting aside how to efficiently implement range locks, I'm going to talk about how to use the range locks inside the Linux kernel to tackle this scalability bottleneck of the memory management subsystem. So, at a quick glance, the virtual address space may seem like a perfect fit for a resource to be protected by a range lock because we naturally define ranges over it. However, this is not the case, and for several reasons. So, the Linux kernel maintains the metadata of every contiguously mapped region within the Linux kernel in a data structure that's called virtual memory area, or VMA. And those VMAs are stored in a red-black tree. So when a virtual memory operation starts, it needs to query this tree to know where its region of interest, on which VMA its region of interest lies within. And the virtual memory operations may furthermore perform structural modifications to this tree. So from the point of view of range locks, it's not feasible to know a priori what ranges to protect. Consider these two mprotect calls, for example, that have those ranges that fall within the same VMA data structure. So if we naively only protect these calls with the input ranges, we will be doing a data race into the same VMA data structure. So to show how we managed to refine the ranges inside the virtual memory, I'm going now to explain briefly our speculative approach. So what I'm showing here is the skeleton or a pseudocode for the skeleton of most VM operations. They are protected by a read-write semaphore that acts as that synchronizes the access to the whole address space. So then they start by the find VMA call, which traverses the red-black tree to find which VMA their address or the region of interest lies within. Then the logic of the operation follows on. So what we do in our speculative approach is we do not anymore use the read-write semaphore, but rather we first protect the find VMA operation with a read range lock that's defined over the input range. And once we find the VMA of interest, we drop this range and acquire a new update range lock, of course if this is an update operation, that covers the whole boundaries of the VMA. Actually, we have to extend the range lock to on both ends of the VMA to handle data races between neighboring VMAs. And furthermore, there also can be an inconsistency between dropping the first range lock and acquiring the second range lock, which we solve by maintaining a global sequence number that's read across both lock approaches. After that, the operation or the logic of the VM operation proceeds as is. And it usually executes read-only operations that from them we can deduce whether this VM operation is going to end up doing or performing structural modifications to the tree that stores the VMAs or not. If there are no structural modifications, then it is safe to continue with the current range lock. Otherwise, if there will be structural modifications, we have to drop the range lock because we do not know now the extent of these structural modifications due to the tree rotations and so on. And after dropping the range lock, we acquire a range lock that covers the full range, so protecting the whole address space to be safe, and we retry without any speculation. And with this speculative approach, we ensure both safety and allow refined ranges for sum of operations, thus allowing room for higher parallelism between the different virtual memory operations. So to show how these contributions worked in practice, we conducted a wide range of experiments. I'm going here to show only one of these results due to the lack of time, which is based on a MEPIS benchmark and in-memory map reduce. So we implemented our list-based range locks inside the memory management subsystem of the kernel together with the speculative approach and compared the following dashed lines. First, the stock, which relies only in the read-write semaphore, then the tree-based range locks that have been proposed in the kernel, and our list-based range locks. So we're showing here the runtime for one of these workloads, so the lower is better, and we can see that our list-based range lock with refined ranges using our speculative approach are capable of scaling to up to 144 threads and achieving like 9 times lower execution time compared to the stock version. And when we look like at the tree-based range locks, even the ones with like refined ranges, we can see that they do not scale beyond 32 threads. And this is expected due to the contention that arises on the internal spin lock. To confirm this, we collected the time that's spent waiting on the lock acquisitions of the memory management subsystem using the lock stats capability of the Linux kernel. We can see here when looking at the tree full baseline that indeed the waiting time increases significantly with the increase of the number of threads, even compared to the stock version that relies on a read-write semaphore. And when looking at the list-based variants, we can see that they incur significantly lower waiting times, which indeed explains the benefits and the performance that they have shown before. To gain more insights on like the different design aspects of range locks and how do they perform in different applications, I would refer you to the paper for more thorough evaluation. And there you will also find like new discussions on, for example, the fast pass, which is very important for the uncontended case that has like, for example, a significant relevance within the Linux community. You can also find discussion on the starvation and memory reclamation. There we also have like the explanation of how you can use the range locks to protect concurrent access of escape lists and so on. So finally, to conclude this talk, we have introduced in this work a new design for range locks that can scale to very large number of threads. We have devised a new approach for incorporating these range locks inside the Linux kernel to allow for more parallelism between the virtual memory operations, and we also showed that Linux range locks are useful beyond the kernel, and they can be used like for synchronizing accesses to concurrent data structures efficiently. And with this, I would like to thank you very much for watching this video.